Sorry, Ilyès. So yeah, let me present you. I mean, I'll read your bio. Yeah, sorry, I forgot. Yeah, so Ilyès is currently finishing his PhD in operations research applied to electrical power systems and markets at CORE, which stands for Center for Operations Research and Econometrics, and at Université Catholique de Louvain in Belgium. He received his bachelor's and master's from Grenoble in France, and he's currently working under the supervision of Dr. Anthony Papavasiliou. And speakers group. So Anthony, would you like to tell us about what you're doing? Is Anthony still here?
Sure. Yeah. First of all, thanks, Ilyès, for inviting us and putting together the event, and for everyone to take the time to attend. We are a group of applied mathematicians, basically in the Université Catholique de Louvain, as Ilyès mentioned, in Belgium. The team now consists of 6 PhDs, also soon to be 5. I consider Ilyès has graduated, although he's still working on sanding his PhD. And his public defense will be in June, if I'm not mistaken. And we work in May. Sorry, oops. So we work on market design issues, congestion management, balancing, scarcity pricing are some of the topics. Transmission distribution coordination in the context of congestion management and balancing, as Ilyès will talk about today. And the other area that we're quite active in is kind of generally advancing analytics methods for power system and electricity market analysis. So large-scale optimization, unit commitment, optimization under uncertainty, stochastic dual dynamic programming, for example. So we try to develop mathematical tools for analyzing electricity markets and operating power systems with a large-scale integration of renewable resources. That's a bit the DNA of the team. Thanks again, Ilyès, for the nice.
You're very welcome. Pleasure to have you here.
Maybe you can tell us also what your team is up to.
Yeah. Okay. Our team. I mean, okay. So we're let's say a small subgroup of the whole power systems teams here in Newcastle. Okay, here in Newcastle we do a lot of things. I mean, we have 2 major projects, as I had told you when we had a discussion, the 2 of us. We have the Center of Energy Systems Integration, and we're doing energy systems integration. So like collaboration between different networks, electricity, gas, and heat. So that's one major topic. We also have Supergen Energy Networks, which again looks into infrastructure and again energy systems integration. I think, okay, there are many projects actually. I missed something. Okay, we have Active Building Center. It looks in demand response, building, modeling, and effect on network. We have UK, China that I'll be working on from July. That's, I mean, a partnership between 3 universities in the UK and 3 in China, and it will be looking at urban energy systems and specifically, I mean, there is a specific component there of soft open points. I mean, maybe you have checked recently. I mean, I had shared with you a paper that we recently published. So, I mean, because the head of this project had actually started this soft open points component, this project will look into it a lot. So these are some projects. There are more. I mean, the group has grown a lot recently because of Phil Taylor, Professor Phil Taylor. Actually, he has left us now. He's in Bristol, but I think a lot of the growth that we see here is because of him. Yeah. So that's it. So over to you, Ilyès.
Thank you, Ilyès, and thanks again for the invitation. So can you all see my screen?
Yeah, we can see. Yeah.
All right, so I can get started.
Yes, please.
So hi everybody. and I'm going to present you some of the work we did with Anthony Papavassiliou. We are focusing on a method for clearing in certain market where we account for both transmission and distribution network, and we have also in the problem we're interested in AC-OPF equations and non-convex offer. So, and I'll explain all of that during the presentation. It should be 45 minutes, a 45-minute presentation, but don't hesitate to interrupt me if you have any questions. Okay, so first, let's start with a bit of context. So I'm sure you all know that the electricity markets are changing. So historically, we had a transmission network with a large unit generating the power that was consumed mostly in the distribution network from consumers. But now we are integrating renewable energy sources, both in the transmission network with, for example, wind, but also in the distribution network through solar PV or electrical vehicles. So now the electricity organization is not as binary as it used to be. And it means that we need to rethink the organization of electricity markets. And this reorganization implies several things. Now the distribution network must be taken into account when we are clearing the markets. The DSOs who are in charge of the distribution network, so DSOs for distribution system operators, will have a more active role. And another key component is how to represent the distribution system, which is more complex and should be carefully modeled. And recently, we've seen a lot of flexibility or transmission and distribution coordination projects in Europe, I named a few national projects and European projects here. And in fact, this work is also entering the scope of one European project called FEVER. So FEVER stands for some weird abbreviations, but the main objective is quite clear, is to promote optimal management of the power grids in future energy system based on renewable sources. So this is an H2020 project that started in 2020. The main coordinator is Intracom, and we are closely working with HENEX, so the Greek power exchange. And the role of UC Louvain in that project is to define the relevant market mechanism and to implement the real-time market clearing platform, and that's what I will present today. There are several challenges related to implementing a real-time market clearing platform by accounting for both transmission and distribution network. First, as I already said, the physical representation of the distribution network should be accurate. So we have to take into account losses, voltage constraints, and reactive power. Also, the scale of the network is not the same. So we were used to only account for the transmission network, and the transmission network typically has a scale of thousands of buses. But with the addition of the distribution network, now it's hundreds of thousands or millions of buses for this part of the network. There's also a challenge related to privacy and decentralization. The transmission system operator and distribution system operators are owned by different people that are willing to cooperate to provide certain service, but some information have to be kept private. So that has to be taken into account when providing a clearing platform. Also, there's an issue related to pricing. So as soon as you, for example, ask for a generator to be activated, he needs to be rewarded. You have to assign a certain price to a certain location. And that in a non-convex and a complex bit structure can be it can be hard to clear such a price. So now that I gave a bit of context, I will explain, I will detail the exact problem that we are trying to solve, which will be called the real-time market clearing problem. I will present the main contribution to tackle this problem, which is based on residual supply functions. I will illustrate the method we developed first on the 3-bus example. Then I will show how it extends to realistic size data, and I will provide some conclusions and perspective. Okay. So what's the problem we are trying to solve? These are first the assumptions we have. So we are in the real-time market. This real-time market can be seen as a market where we need to activate some transmission or distribution reserves to adjust a predetermined dispatch. The time horizon that we consider is typically 1 hour, and we consider that so the decisions are taken every 15 minutes. So the first decisions are dispatch decisions, and let's say second, third, or fourth decisions are advisory decisions. For the network, we will consider that the transmission network is meshed, and a common assumption is to assume that the DC approximation of the power flow equations holds in the transmission network. And we will assume that the distribution network is radial, and we want, since it's a different scale, different network, we want the true AC power flow equations to be satisfied in that network. Okay. Concerning the roles of the different actors that we have in this market, so as I said, we have the TSO and the DSO. This is, I already talked about them, so they operate their side of the network. So transmission for the TSO, distribution for the DSO. We will consider that the actors for, so we'll consider generators, and we will call them balancing service providers, since we are in a real-time, in a reserve type of market. We will also have a balancing responsible party. There can be seen as owner of non-flexible assets, so it will typically be the demand. And we add an extra role, let's say, because we don't exactly know how this service will appear in practice, but we call it aggregation disaggregation service, so for ADS. And the role of this agent will be to aggregate the distribution network, and in particular the BSPs, the BSP offers at the transmission and distribution interface. This is the role. This is by using the residual supply function. I'll explain what it is. And it should also coordinate with the DSO when we disaggregate the accepted offer. Okay, so if I have to draw a picture of how our framework works, so just to give you an idea. Okay, so the first step is for the ADS to compute the residual supply function. This residual supply function is based on the bids that he received from the distribution network. This residual supply function is then sent to the transmission network, as well as the bid from the BSPs in the DSO. This will allow to clear the transmission market. Once this transmission market is cleared, dispatch decisions are sent back to the BSPs in the transmission, and the market results are communicated to the DSO, who is now responsible for disaggregating. And disaggregation means sending dispatch decisions to the BSPs in the distribution network. And in step 4, we have all the actors settling. So we just send the price or remunerate the actors that have been active in the market. The bottom line is the following. What we want is to implement a practical clearing platform, and several features have to be implemented. So we want the decisions to be optimal or near optimal. We want the dispatches to be feasible, in particular in the distribution system where we model the distribution network with AC power flow equations. We also want coherent pricing, even if we have a complex bit structure. I will explain what it is later. We also want the market to be cleared fast, so in less than 5 minutes, let's say. And one last thing is that we want the privacy to be preserved, which means that the TSO and the DSO should only share border information. Okay. So to do so, the main problem that we consider is AC optimal power flow. The goal of this problem is just to find the cheapest way to generate enough power to satisfy the demand on a power network without, of course, violating technical constraints. We have a set of buses, a set of lines, and a set of generators or BSPs. And the classical variables are the real and reactive power injection, the real and reactive power flow, and the voltage, angle, and magnitude at each location. Okay, so if we have to write AC optimal power flow, we do it as follows. So we're trying to minimize some generation cost, and we have the power flow equations here. So first, we have the dispatch instructions, so PJ and QJ. The other variables are the operational decisions, so the flows V and theta. We have some fixed load that are imposed by the BRPs. J and B are typical network properties, so G for the conductance and B for the susceptance. So as I said, we are trying to minimize some generation costs. The first two constraints are the real and reactive power balance constraints that will later be aggregated as Fi of x equals to 0 for each bus, so it's different for each bus. Associated with these constraints, we have the prices, so LMPs, and they can be seen as dual variables of these constraints. And the last two constraints here are the flow definitions. Okay, and the non-convexities, so AC optimal power flow is non-convex, and the non-convexities come from the flow definitions, in fact, here. So you have a squared on the voltage here, you have a sine with the angles here, so it's a non-convex problem. And I did not finish writing the constraints, so here are the power balance, the flow definitions, but in addition, you also have some technical constraints on your operational decisions, so V and F, but also on your generation decisions, so P and Q. The bottom line is that we can write the problem as minimizing some generation costs subject to power balance constraints, operational constraints, and generation constraints here. Okay. So this will be used for the distribution network. But for the transmission network, I said that we can approximate it by using the DC approximation. And this approximation holds, is explained by doing the following. So we assume that reactive power is not mandatory to model. And the other assumptions are the following. So we'll assume that the conductance is typically 0, that the voltage magnitude is approximately 1, and that the angles are small, so the sine can be approximated by a difference of the angles. All of that allows for removing some terms and changing ones, so the product of voltages will be equal to 1 and the sign will be replaced by the difference. And the conclusion is that the DC-OPF is a linear approximation of the power flow equations. So now let's transpose that to our transmission and distribution setting. So we're still trying to minimize our generation costs. Generators can be all over the network. We have again, power balance constraints, operational constraints, and generation constraints. Of course, in the transmission network, we have the DC approximation, so less variables. But in the distribution network, we have the true AC equations, so much more precise and with some non-convexities in here. Now we also have to make the link between those two networks. So we assume that we have only one interconnection between the transmission and the distribution. And what we do is that we will assume that there's only one variable called F, and that we will duplicate it in both networks. That is just for ease of modeling, and you will see why later. Okay, and something maybe I did not say is that I will make the presentation with only one transmission network and only one distribution network, but this can be generalized with one transmission network connected to several distribution networks. The only assumption we make is that there's only one line between one transmission network and one distribution network. Okay. On top of the power flow modeling that we have for transmission and distribution, we will introduce some complex bit structure. So what it implies, even if I'm not detailing the bit structure, is that it introduces one or several binaries for each power injection J. So what it means is that for each generator, so for each red node here, you will have one or several generators. And for what it implies is that for each generators, we introduce a certain number of binary variables. And typically what you can model using that is block bits. Okay. In addition to this, so I presented the problem on a single time step, but in fact, I said that we consider 1 hour ahead, so we have 3 or 4 time steps. So we need to account for that in the modeling. What it implies is that some of the constraints have to be satisfied at each time step, so it does not introduce intertemporality. This type of constraints are typically the power balance constraints that need to be satisfied at each time step, but also the operational constraints. So for example, if you have line limits, this line limit has not to be exceeded no matter what the time step is. But for generation constraints, there can be some intertemporal constraints. And as example, you can think of RAM constraints or minimum duration of a bit, or also some exclusive bits. And this intertemporality adds a layer of difficulty to solve this problem. Okay, so if we want to write the whole problem in a compact way, we do it as follows. So we're trying to minimize some generation costs over a certain time horizon. We have the power balance constraints that need to be satisfied at each time step for each node. We have our decisions that needs to be in a certain set. This was for the transmission, but we have the same for the distribution, but think that this part of the problem is more difficult. And we also have these interconnection constraints. It's just saying that, so it's just representing this line here. Okay, so at the end, this problem is a large-scale non-convex mixed integer problem that we have to solve. And when I say solve, the decision that we want here are dispatch decisions, so that can be seen as the primal. So it will typically be the generation, the flows, etc. We also have to clear the activation decision, so to know which bid is accepted. And in addition to this primal information, we also want prices. So we want to have a certain valuation of a power balance when it's cleared. And the question is, how can we solve this real-time market clearing problem? And the most straightforward way to do it is to use the second order.
Excuse me, Ilyès.
Yes.
So you're allowed to ask questions as we go.
Yes.
Is that okay
sure,
if
sure,
I ask?
Yeah.
On the last slide, on the previous slide,
Yes.
there is these two last constraints, and you have a mu and minus mu.
Yes.
What is it? Is
You're
it
right.
dual variables?
Yes.
So and what do they represent? Do they also represent LMPs?
Yes.
At this at the interconnector?
Thank you for your question, Timo. So yes, so here the lambdas represent prices for certain nodes, but since I'm going to present a decentralized framework to solve this problem, I will also need a dual information of the interconnection, and that's why I'm introducing this mu here. So it's not properly a price on the location, but it's an idea of the pricing of the line here. And I will explain how I use that later in the presentation.
Yeah, but physically it means the same, right?
Yes, physically
the same LMP,
yeah, it's the same idea. So
it's at the interconnector.
Yes.
Right?
So I don't want to say it's a dual variable, because when you have binaries,
variable then.
But I mean, when you have binaries, it's kind of I mean, you don't have really a notion of duality. That's why I don't want to say dual variable, but but it's the same idea. It's an idea of the price of this constraint, evaluation of this constraint. And
okay,
this is the same as LMPs. All right. Is there any other question, maybe, before I continue? Okay, I'll take that as a no then. All right. So now that we have this problem, how can we solve it? And the most, I mean, if you want to solve it, let's say rapidly, you can use the second order cone relaxation of the AC-OPF in the distribution network, because in fact all of the non-convexity come from these constraints here. So it's the generation and the operational constraints in the distribution network, and in a radial setting, we know that the second order cone approximation relaxation is very effective. And so if you want to solve this problem in a centralized fashion, let's say, you will first solve the mixed integer second order cone problem that you have in order to deduce some in order to deduce the activation, then fix the activation to its optimal value, and then solve the SOCP, the second order cone problem that is left, in order to deduce your dispatch decisions and your dual decisions. But you might end up with an X, so an X decision that is partially feasible. So another alternative is to add a third step, which recovers feasibility if XD is not feasible. So you do the exact same two steps, and if you identify that your XD is not feasible, you use a nonlinear solver like IPOpt to get your XD. But the issue with these two approaches is that it cannot guarantee the privacy of the TSO and the DSO, because if you want to implement such a framework, the TSO would be in charge of clearing the whole market. Also, an issue that I didn't talk about is the scale also of the problems. Solving this problem in a centralized fashion might be computationally heavy.
Ilyès, sorry to interrupt again. Natalia has a question.
Sure. I cannot see the.
Okay. So I'll be saying, but
Okay.
Timur was here in the office, so I told him offline.
Okay.
Yeah.
Sure.
Okay, Natalia, go ahead.
Hi, thank you very much, Ilyès, and thanks, Ilyès, for this very interesting presentation. So I had, maybe it's a simple question, but because you said, that you now you have put this red block, so I can't really see what it says underneath.
Okay, sorry.
But you said, recover feasible dispatch if it is not feasible. Is it, if it's not feasible in the sense that you run, like, for example, I don't know if you use what type of software you use, and then it just says infeasible, or is it how do you check that? I guess that's my question.
Okay.
Thank you very much.
Yes, so thank you for your question, Natalia. So when I'm solving the relaxation, I get, so since it's a relaxation, the dispatch I obtain can be unfeasible in the physical sense, like, so I will have a solution, but I still have to check if it satisfies the AC equations of power flows. And if it's not the case, then I will have to do an extra computation, which consists in solving the actual problem with the AC equations.
You mean the non-convex ones?
The non-convex, exactly, yes. The non-convex.
So you solve the MSOP, which is an
Yes.
optimization.
Yes.
And then you take the X and you put it in the in the non-convex.
Yeah, I want to check if this X is feasible for the non-convex case, for the non-convex.
Okay.
Sometimes it is, because the relaxation is very efficient for radial networks, but sometimes it's not. And if it's not the case, then I have to do this extra computation, so which is solving the non-convex problem.
Okay, thank you. And do you use like and a last question, and I'll allow you to continue. Do you use like Math Power to do that? What do you use to check that?
So I don't use. So yeah, the data I tested is not related to Math Power, so no. But so maybe I can say it now, yeah, because I'm sure I will forget to say it later. But for the second order cone programs that I'm solving, or the linear programs that I'm solving, I will be using Mosaic, so which is one of the competitor of Cplex or Gurobi.
Yeah.
And when I will have to solve a non-convex problem, I'm using IPOpt.
IPOpt. Okay. Thank you very much, Ilyès. Thank you very much, and thanks, Ilyès, also. Thanks.
But Math Power also runs IPOpt, no?
Yeah, it runs IPOpt, but I think it's Math Power comes with a set of instances, and I mean, I just
sure. Yeah, we're not porting our data into Math Power, but the underlying solver, I guess, is.
Yeah,
I don't know if they've done any particular tweaks to the basic IPOpt thing, or.
I'm not sure. I think you just use IP. You can use IPOpt. You can use another nonlinear solver.
Within the settings of MATLAB.
Yeah, exactly.
Okay, I see. Then definitely they haven't done any changes. Okay.
Okay. If you have other questions, maybe it's the right time to ask them.
I cannot see anyone else having raised their hand, so I think you can go on.
Ilyès, just let me know when someone raises.
Yeah, I'll let you know. Thank you very much.
Because I don't see it when I present.
No problem.
Okay, so all right. So as I said, doing what I just said cannot be implemented in practice because of privacy issues and scaling issues, let's say. And now what I will suggest is a decentralized framework, and it's based mostly on residual supply functions, and I explain now what it is. Okay, so this will be a 4-step procedure, and I'll explain each step as follows. So first, we are in the distribution network, and we want to build the residual supply functions, and this residual supply function is a way of evaluating the interface flow here. And to do so, we will assume different levels of the flow. So here I will be solving a residual supply function problem for a certain level of flow f tilde that has been fixed, that we choose. Between one, we will have n value to test. Let's say this is the first one we want. So, and the distribution problem that we are solving is the following: trying to minimize the distribution generation costs subject to power balance decisions, power balance constraints. Note that the set of constraints, we are using the second order cone relaxation. As I said, we are fixing the flow to a certain value, and we will also assume that we relax the binary variables. The binary variables, yes. And in fact, so we are solving that for a certain value of the flow. And the only thing we will deduce from this problem is the dual variable associated with this equality constraint. And this will allow us to place this point on this residual supply function curve. And you might claim that this is an over approximation of what's going on in the distribution network, but we noticed from previous work of Anthony that doing such an approximation can be sufficient to have satisfactory results. So now that we computed this RSF, so this RSF is again, it's certain flows for which we associated a certain price. We will send it to the residual supply function. This can be to the transmission network, and this can be seen as an additional bit that is sent to the transmission market. So, and to send this, so as I said, so it's plugged here in the objective. Here we just have to discretize the different levels of flow that are considered. And we solve now the transmission problem with the residual supply function. So we have classically the power balance constraints, the dispatch and activation variables that are in a certain set, and again the flow definition here. From this transmission market, when clearing this transmission market, what we deduce is the dispatch decisions for the transmission network, the activation decisions for the transmission network, but also the interface flow and a price associated with this interface flow. Okay. Now that we have deduced the interface flow, we are able to compute the dispatch in the distribution network. And to do so, we fix, as I said, fix the interface flow and then clear the distribution markets. And that will allow us to have a complete primal and activation solution. But don't forget that we also have to compute prices. And to do so, we solve, again, one transmission problem and one distribution problem. And it's slightly different from the ones I've been showing, because this time the flow is not fixed and we are penalizing it with a certain valuation. And the valuation we use is the previously computed interface price. This can be, you can see this and be a bit skeptical about it, but I will illustrate why we are doing this on an example. And solving this problem will allow us to deduce the lambdas, so the LMPs for this problem. Okay, so this was maybe a bit fast, but I'm sure it will be clearer on the 3-bus example that I will show. So we conducted numerical experiments first on the 3-bus example, and then we extended to some realistic instances. Okay, so the 3-bus example is the following. Here we have one transmission network and one distribution network. Only one node in the transmission. All of the buses can be our BSPs. We have a 1 megawatt node here, 1 megawatt load, sorry, here, and a 0.2 megawatt load here, and we have a line limit on the line connecting the two distribution buses. So here we won't assume any binary variables or any accurate modeling of the distribution. We'll just assume that everything is linear, and if we want to write it as an optimization problem, this is how it looks. So you're minimizing your generation cost. You have 3 power balance constraints, you have capacity constraints on your generator, and you have also line limits on your flow connecting 2 and 3. Okay, so what happens if you want to solve this problem using our framework? The first step is to build the residual supply function. So to do it, you only consider the distribution network, so you don't have this the offer from the transmission generator. And what you are just doing is assuming different levels of flow. So this is one discretization that I choose. And for each discretization, so each point of the discretization, you will evaluate the cost of flowing this amount of power. So for example, let's say that here I want 1 megawatt at this level here. What will happen is that to do so, you will ask for BSP3 to produce 0.7 megawatts, and for this BSP to produce 0.3 megawatts, because then you will be able to satisfy this load here and let's say the superficial load that you are requiring here. And since let's say that the most expensive BSP is this one, you will assign a value of 15 euros per megawatt, and that's why around 1, the residual supply function is equal to 15 euro per megawatt. Okay, and then if you want to have, let's say, a complete representation of some kind of residual supply function, you can add the offer from BSP1. Okay, so this is how we build the residual supply function. That's the first step. The second step is to clear the transmission markets now that the distribution network is aggregated. So what we want is to satisfy this 1 megawatt load, and what we have is this complete residual supply function, let's say. So you want the cheapest way of satisfying this load. How do you do that? By just drawing the 1 megawatt line. So you know that you are, so by doing so, you are asking 1 megawatt from the distribution network. Okay, this has been cleared. You are now communicating the information to the distribution network. This is what is happening. So requesting 1 megawatt, you don't have access to the offer from the transmission network, and you are disaggregating your distribution network. So you're asking your BSP2 to activate 0.5, BSP3 to activate 0.5 plus 0.2 to cover this imbalance here, and you are also deducing your flows. Okay, so now we have a solution, a partial solution, because it's only the primal solution. But as I said, we also want the prices. And this is the goal of the first step, the fourth step of the procedure. And I'll explain how it works. So the optimal solution of the example is the following, so it doesn't really matter here, but...
Ilyès, sorry to interrupt again.
Yes.
I'm just a bit conscious of time. Do you think you will have finished in 5 minutes?
I will, yes. I mean, I have 6 slides left, but I can do it more quickly. For sure.
Yeah,
so I
yes,
have
please.
5 minutes left.
Yeah,
Okay,
just to have to leave some time for discussion.
I agree.
Thanks, Ilyès.
Sure. Okay, so we have the primal solution. We fix the interface flows and what's going on. So once you fix it and you want to solve the transmission problem, here is what you get. If you try to solve this problem, you indeed end up with P1 equals to 0 because you fixed your flow to -1. But what happens to the prices? You get the following KKT conditions, and this set of equalities can provide you different solution for lambda 1, which shows that it's not obvious that it will be equal to 15. And what we do to ensure this property is to solve the extra optimization problem that I showed. So by doing so, you will end up with this KKT condition replaced by this one. I don't know if it was completely clear, but we can discuss it afterwards. Okay, you have, so bottom line is that for the 3-node example, we have a primal and dual solution that you can display some settlement table, but since we don't have much time, I won't comment on it. Okay, this has to be extended obviously to more realistic instances. These instances we had access to these instances from the SmartNet project, so it's representing 3 Italian test cases and 1 Danish test case. So the first one is in the order of magnitude of tens of thousands of variables and constraints, while the 3 other ones are much larger, more in the size of hundreds of thousands of variables and constraints. Okay. And these are the results. These are the results we get. So maybe I will quickly go on what we have. So I have the test case, the approach, the objective value we have, the gap to the relaxation, the violation of the constraints, and some measure of the quality of the primal and dual solution and the time. So first, and sorry about the approach here. Hybrid is the benchmark method, so relaxation benchmark and residual supply function. The first thing to notice is that the relaxation solution and the other solution are quite close, of course, closer to the hybrid in terms of objective, but we can see that the residual supply function is not working so bad. And the other thing to notice is that the relaxation solution provides some infeasible dispatch. The maximum violation should be less than 10 to the minus 6. The other thing is on the lost opportunity, because I did not explain what it is. Maybe we can comment on that later. And also in terms of time, what can be bothering for the residual supply function approach is that it goes over the 5-minute requirement, and it also goes over 5 minutes for all of the approaches on the Danish test case. But luckily, even if I did not comment on that yet, since we have so since we are solving transmission and distribution problems separately, there is a lot of things that we can parallelize in the procedure I showed you, and we managed to show that for this particular instances, if you get at least 16 processor, you are able to go under the 5-minute requirement. Okay, and also I draw some additional pictures on the additional tables and a picture for the Danish test system. We can discuss it later if you want. So just to conclude the presentation, we have developed and implemented a centralized and decentralized approach to attack the problem of integrated transmission and distribution balancing markets. And our preliminary large-scale results show some promising outcome. All of this work is part of my PhD dissertation and has just been submitted to IEEE transactions on power systems. And future directions of the work will focus on alternative methods for pricing in a non-convex setting. So Nicola, who is also in the call, will be mostly working on that in the next few months. We also want to test the approach on other test systems. We want to elaborate how such a platform can enter the scope of European balancing and congestion management. And also we are currently analyzing the potential of the residual supply function in a coordination between European, in a context of coordination between European TSOs. So thanks for listening, and I'd be happy to take some questions in the future.
Thank you, Ilyès. Thank you very much. It was really interesting. So Timur has had a question, so I think he's eager to ask. So Timur, please also, because Timur is working actually on a project I forgot to mention before, if you could mention this, Timur, because you're working on a project with Northern Power Grid.
Yeah, thanks. Yes, thank you, Ilyès. Thank you very much for the presentation, and for me it was absolutely clear what you have presented, and I don't know why. Well, I think it's, well, you have a very good presentation skills, but also it's maybe due to the fact that I'm working on the similar topic right now, but your presentation skills are very good.
Thank you.
Yeah.
Thank you.
And in general, I have a comment like that your approach is quite interesting and nice, and the reason I'm saying that is that I'm using the similar approach. Yeah, so this is one of the reasons, and I also liked the way how you deduced the problem decomposition from the general formulation, because in my work I didn't do it. I just formulated it in a distributed way, just following the common sense, but I end up with the same formulation, with the similar formulation, because I'm working on, well, not on the exact same problem, but on the similar problem. Yeah, and I probably have one question regarding the slide 33, and it was not clear for me what is RSF 100 and 300. What's the difference between this?
So, yeah, I didn't have the time to explain that, but the idea is just that here we use the 100 points to discretize our residual supply function, while for the three others we used 300 points.
You mean 100 discrete steps for your supply curve? Or
exactly, yes.
Okay.
And
okay, and what is and why is this? You have this very big gap.
For
well, I mean that I can see that you have the gap. What does this gap represent? Does this represent?
So it's the difference between the relaxation solution and the actual solution that we get. So yeah, it's much smaller for the hybrid version.
Difference in the objective function?
Yeah, in the objective value, yeah.
Ah, yeah. So, yeah, well, it looks like a big number, but if you put it in the relative value, I would assume that this would be very small.
Exactly. And so it's not that small in a relative way. I mean, it can be large, so that's why we'd rather represent it this way. But the other thing is it's small compared to, so this PLP number is, you can see it as the volume traded in terms of, yeah. So yeah, it's just to show that this number is pretty small compared to the to the amount of money that has been exchanged here in a way.
Yeah, I think that the main cause of this difference is because you consider discrete functions.
Exactly, discrete. So yeah, there is that, the fact that it's discretized. Also, it's challenging because you have several time steps, so you have some kind of coupling between the time steps. So knowing how to discretize is also tricky. So I did not elaborate on that, but I can, if you're interested in knowing why I have some, I mean, knowing more in the framework, I can share with you the chapter of the thesis that I wrote.
Yeah, that would be nice. Well, I wouldn't mind having a whole thesis because it looks like a very interesting work and relevant to the things that I'm doing. But anyway, good job and well done. I like the presentation and the work you've done. Very nice. Thank you.
Thank you very much.
Thanks, Timur. So just to mention to everyone, so thanks everyone for attending. Timur, please could you plug in your headphones again? Sorry, I think I could hear my voice twice. Sorry, Timur. Thanks everyone for attending. I mean, I can understand that some people will have other meetings, so feel free to go if you have another meeting, or feel free to stay if you want to discuss maybe 5 more minutes.
Sure. I'm free, so yeah. I have 15 or 20 minutes if you want.
Nice.
So
thanks, Ilyès. Yeah, thanks, Ilyès. Adib, are you here?
Yes, I'm here.
Hi, Adib. So, I mean, I think you're interested in this topic.
Yes.
Yeah. So, do you have? And Adib, by the way, has lived in France for 5 years. He did his PhD there. So,
Université de Joseph Fourier. Yeah.
So yeah, I was in Grenoble also. So same place.
So exactly. So I'm interested in this, and especially now I'm working more about energy market, which is more it's about gas and electricity markets more than only electricity. So something it's interesting topics for me. So, but I will contact you if like letters for if I have more questions or any something related to my work as well. Thank you.
Thanks, Adib. Thanks a lot.
Thank you.
So, Timur, I would like you to present a bit about the project you're working. Timur, are you there?
I was about to leave because we have this weekly meeting on the project that I'm working.
Yeah, but you know, it's for the demonstration of the project.
But
so.
I can try and say what we do on the, well, so basically we work on the industrial project called customer-led distribution system, and we look into the customer demand flexibility and to determine its potential and its potential in terms of capacity and in terms of economic value. And so what I do in this project, I apply game theoretic approaches in studying the behavior of market participants and this flexibility markets, and look at the values and equilibrium prices that are expected on this types of markets. Yeah, so if you are interested in this, we can take it offline and discuss it in more details, but I don't know. Just let me know.
So how is the project called? Sorry.
It is called Customer-Led Distribution System.
Okay.
Yeah, so it is industrial project with our local distribution network operator.
Okay. Yeah, definitely. I think it can be interesting. I'm kind of
and in terms of well, the work that you did, well, I actually have a couple of thoughts on how it can be developed. So the first thing is that instead of this decomposition by using this residual supply curve, I think it would be possible to incorporate some formal optimization methods. For example, ADMM. For example, I don't know if you're familiar with this.
Yes, I am. Yeah.
Yeah, so I have some experience in that, and I feel that it can be incorporated in this formulation.
But so if you're the only kind of, we didn't want to go for a kind of iterative method like AGMM because we feared like
it could be time consuming, I understand.
Time consuming, but also, I mean, but it's a nice way to decompose the problem. What we like about the residual supply function that we developed is that you are asking, you know, there's only one way of communicating the information. Once the residual supply function is built, it's sent to the transmission market that then is cleared. Then you go back to the distribution and then it's cleared. While I think in an AGMM fashion, you will have to do some bouncing between.
Yeah, you would need to exchange this dual variable between the two optimization problems
several times, and I think this
until
can be
it converges to some point. Yeah, this is the idea of ADMM. And another point, another suggestion that I might have, and this is exactly what I'm doing right now, is incorporating some strategic bidding into this framework so that your residual supply curve is not static, but it can be, it can deviate from the initial value based on the based on the outcomes from the previous market clearing. So this can represent the strategic bidding of the flexibility providers. And in some points, when you have, for example, a lack of competition, you can see that some simple strategies can lead to the to market failure, for example. And this is an interesting result. Well, if it's possible to illustrate this, I think this would be a very interesting result, and you can try different market clearing principles in this. Yeah, so this is my some of the ideas I have on your topic. And if you are interested in developing this or discussing this, yeah, I would be happy to do it.
Definitely interested in discussing this. So yeah, maybe you were not. I think you were here, yeah, when we were discussing that. So yeah, as I said, I'm wrapping up the PhD now, and I will be starting to working at NG in April. So I'm not really. I mean, I don't have much time left to work on this, but I would definitely be interested.
Well, I've heard that you are leaving the academia stuff, but well, this is also FYI for your colleagues, which I think
they are listening carefully. So I mean, definitely get back to you if some of us are interested in that.
Yeah, and I guess
I take down I've taken the note of the ID, so because I will be the one maybe like working a bit on what Ilyès has been doing so far, even if for the moment it's more focused on a side question, like on the pricing issue. But I agree that this kind of gaming and bidding behavior, like to see how this can work, is also something interesting. So thanks.
Yeah, I would be happy to discuss it. Thank you.
Yeah, feel free to contact each other, I think.
Yeah, I would definitely send the thesis to Timur since you're interested, and like that we can maybe exchange for the emails and see if potential further discussion is can be organized.
Yeah, so thank you very much. Thanks, Timur, for the question. Thanks, Ilyès, for the very nice presentation, and good luck in your final presentation and the paper submitted to IEEE Transactions Power Systems.
Thank you.
So generally, it sounds that you're a group that you are very good in maths, so we'll have you in mind. We might contact you.
Sure. Anthony would be happy to.
Yeah, definitely. So Anthony, maybe he's back again. He had a call. He mentioned he had a call. Definitely, I mean, we'll be in contact you. Okay, Timur will definitely be, but in maths terms, we'll be very happy to contact you to have advice from you.
Thank you.
Because you seem to do serious stuff. Right. So thank you very much. I don't know if anyone else has any other questions. Yeah, good luck in your defense from Adib.
Thank you.
Thank you very much, Ilyès. Thank you everyone for attending this workshop.
Yes, thank you for your interest in that, and thank you for the invitation once again, Ilyès. We'll be